So today we are very happy to have Lukasz Fidkowski, who will tell us about lattice gauge theories from Symmetry Disentanglers. We're going to dinner, and if you're interested in dinner, please send an email to Nati, and we're meeting at 6 here.
Okay, great. So yeah, thank you very much for the invitation to speak here. I'm going to be talking about some recent work with Ryan Thorngren and John Preskill on Chiral Lattice gauge theories from Symmetry Disentanglers. So the plan of the talk, first of all, I'm going to give an overview of what I mean by chiral theories and sort of the ideas that have been used to try to put them on the spatial lattice. So just a couple of things to keep in mind. Throughout this talk, I'll be talking about the spatial lattice only. So I'm interested in spatial lattice. I'm interested in local degrees of freedom, living on the spatial lattice, and Hamiltonians that realize certain interesting theories in that IR. So for me, chiral theories, roughly speaking, will mean that there is, first of all, a symmetry. And for my purposes, I will never gauge the symmetry. For my purposes, the symmetry will be a global on-site symmetry. It will be a global symmetry, then we'll see what it made on-site. But there's a global symmetry, and roughly speaking, the chiral theories that I'll have in mind will have several different low energy sectors. Each of them will be anomalous under this, having a Hooft anomaly under this global symmetry, and the Hooft anomalies will cancel between the sectors in some interesting way. That's in particular not left-right symmetric. So yeah, I'll get an overview of that, and then I'll discuss our strategy for realizing these theories by constructing so-called symmetry disentanglers. And then I'll give some examples. So, this work? So I'll have examples in 1 plus 1D and in 3 plus 1D. In 1 plus 1D, there will be exact solutions. In 3 plus 1D, there will not be exact solutions. There will be a heuristic involved, but I'll sort of point out exactly where things become non-exact in 3 plus 1D. And then finally, I'll conclude. Okay, so just to all get grounded, I figured I'd start sort of in the simplest possible setting of a fermion in one spatial dimension. This has sort of all the nice properties you could ask for. And in the back of my mind, really, I have a condensed matter picture of a tight binding model. So what I've drawn here is a band structure. There's a Brillouin zone, crystal momentum. Blue thing is a band. So just imagine some kind of translational invariant tight binding model that preserves, overall U1. And in general, you can imagine there's some band structure. Maybe it looks like this. Put a chemical potential there, 0. What do you get? Well, the solution to this Hamiltonian is that it's a free Fermi gas in one dimension. And the low energy excitation, so the ground state consists of all of these states being filled, and the low energy excitations are just a single right mover and a single left mover. Okay. So as far as low energy excitations are concerned, this is a Dirac fermion. There's a right mover and a left mover. But it's realized in this way, in this tight binding model. You can think of these as 2 Fermi points of a Fermi. So this has a microscopic UV symmetry, the one that I mentioned. It's by UV symmetry, I just mean, literally it's a symmetry of the microscopic tight binding model, just overall charge conservation. But of course, in the low energy theory, there's an emergent symmetry, which is just the difference between the right moving and left moving charge. Or said in other words, the left moving and right moving charges are independently conserved at low energies. Now, of course, these things have a mixed anomaly. These two symmetries have a mixed anomaly, so it's impossible to realize both as microscopic on-site UV symmetries. And it'll be useful to, this. I mean, but just for me, it'll be useful to review the condensed matter argument for the mixed anomaly between these two symmetries, the symmetric and anti-symmetric combinations of left and right moving charges. So the idea is, this is just the Laughlin flux insertion argument. Put your system, this is the real space. So you put your system on a ring, these are the sites. So your tight binding model on a ring. And to see this mixed anomaly, you can gauge the vector symmetry, by which I mean something very specific. Because I have an on-site symmetry, I can do a minimal coupling to a U1 vector potential on the lattice. I can introduce U1 vector potential degrees of freedom on the lattice. It's Gauss's law. And just imagine a flux insertion process where I insert some flux inside this ring. So if I do that slowly, just standard minimal coupling shows you that inserting a flux, or inserting some vector potential along here, is equivalent to twisting boundary conditions for single particle states in this way. And so as you do this slowly, all these states shift as you insert flux. And at the end of the day, you end up tunneling a right mover to a left mover, and that shows that the axial vector charge is not conserved. And this is a way of explicitly seeing the mixed anomaly between these. So in particular, it's impossible to realize both these microscopic on-site symmetries meeting with the Hamiltonian, because if you could, then you could just gauge the whole thing without a problem, and you wouldn't see this something. Okay, great. There's another perspective that's useful in thinking about these kinds of problems, which is this anomaly inflow perspective. So here, both symmetries, the vector and the axial, are realized as microscopic on-site symmetries. The price to be paid is that an extra dimension is introduced. So here, I imagine that my original 1 + 1 dimensional system lives on the edge, but there's an extra bulk that's introduced, and the bulk is non-trivial. So specifically for this example that I just gave, the low energy theory of a single left mover, a single right mover, drop fermion, one can take the bulk to be just a stack of Chern insulators, Chern insulators with Chern number +1, that gives you the right mover, Chern number -1, that gives you the left mover. So in this case, the symmetry is realized on site, but the bulk has a non-trivial SPT is the bulk you can think of as a non-trivial symmetry protected topological phase, or SPT, of this product symmetry, and its inflow action is just this. So that's the left mover, that's the right mover. These are just the effective actions per Chern insulator. This is certainly related to this idea of domain wall fermions. But the important point is that the low energy degrees of freedom live on the edge. This bulk is gap, but it's somehow stillness. Okay. Very simple. So let's just look at something very simple in here. Let's suppose that we want to focus on just one U1 symmetry. And I really want this to be a U1 symmetry, not an R symmetry. So I'm going to take a linear combination of, so I've introduced these Q left and Q right, which are the symmetric and anti-symmetric combinations of the axial and vector charges. And let me just take a general U1 subgroup, this linear combination. Okay, so if I want to probe the response to this particular U1, I just substitute, A left is this, A right equals this. So, basically I'm sort of declaring a new U1 symmetry where these fermions carry charge M and these fermions carry charge N. And this is the response. It has this M squared minus N squared coefficient. Nothing interesting is really happening here. If M is different from N, then this signals an anomaly, a self-anomaly of this particular U1 symmetry. And it means there's a non-trivial bulk. And so this means that it should be impossible to realize this, this theory with a single right mover and a single left mover in such a way that this single symmetry now is realized on site. It just has this self-anomaly. But in the cases where this coefficient vanishes, that's just M equals plus or minus N, you can sort of immediately see that you can realize effectively quasi one-dimensional theory with only these with only sort of one domain wall's worth of energy of low energy degrees of freedom by just gapping out these so-called mirror fermions or doublers. So there's this idea that domain walls introduce the original theory and some set of doublers on the other side of the domain wall. And there's this important idea that gapping out the doublers is effectively equivalent to realizing one's original theory. And so here, when M is equal to plus or minus N, it's kind of straightforward to gap out the doublers. If M is equal to N, you can just backscattering term from left to right. If M equals to minus N, you just do a particle transformation on one of these and then also introduce that same backscattering term. So sort of nothing interesting is happening here, sort of everything straightforward. But now let's introduce a slightly more complicated setup where I just have N copies, capital N copies of the setup that I just introduced. Okay, so you can either think in terms of this anomaly inflow picture where you have N a stack of n of these original systems, or you can think of a stack of n one-dimensional systems. Doesn't really matter. But now you have a much larger symmetry group because there's the axial and vector symmetries of each one of these n stacks. So there's sort of 2n different U1 generators and a bunch of mixed anomalies. And now you can consider, again, looking at just some particular U1 subgroup there, some linear combination of these with integer coefficients. So then the condition for the self anomaly of this to vanish is just sum of m squared minus n squared is equal to 0. It's the same condition that we had before, except we add over the entire stack of layers. So, in SVT language, this is just a this whole stack is just a single 2 plus 1 dimensional SVT of a U1 symmetry, and it's conjectured that the only sort of non-trivial invariant that characterizes those is the Hall connectivity, which is just this. So one can conjecture that this thing can be realized as a microscopic on-site symmetry precisely when this is 0. But now there are sort of non-trivial solutions to this. With a single, when n equals 1, there's just trivial solutions, but when n is larger than 1, like 2, for example, there are non-trivial solutions. So for example, there's this famous 3450 theory when n is equal to 2. So you can just choose these integers in this way. And because these form a Pythagorean triple, this equation is satisfied. And so based on that conjecture, you would say that this theory should be realizable, equivalently gappable, symmetrically gappable. But it's not obvious how to do that from sort of just a simple field theory picture, simply because you can't write down any free fermion terms that are symmetric and gap out the theory, because now sort of all these different chiral movers carry different charges. And so scattering from one to the other is going to violate the charge conservation of this particular U1 generator. You're going to try to scatter a charge 3 object or a charge 4 object or something. So there's no relevant perturbations you can write down. And so, so what does one do? Well, one has to sort of crank up some irrelevant symmetric perturbation, make it very strong, and the regime of validity of the field theory, crank it outside of the regime of validity of the field theory, and just cross fingers and hope that gaps out the doublers in the symmetric way and doesn't affect the original fermions. And there's numerics that suggest that this does indeed work. There are other approaches to realizing this, Euclidean lattice, using supersymmetry, and also Sahand has a paper on this that came out just a few days after ours. But let me. So I'm going to give a punchline. I'm going to give our perspective for how to construct this in an exactly solved model. How to construct this 3450 theory in an exactly solved model. Before I outline the general strategy for that, let me just briefly mention the situation in 3 plus 1 dimensions. So, short description, same kind of story. In 3 plus 1 spatial dimensions, you can make you can also consider a setup with some wild fermions, just like in 1 plus 1 dimensions. You can make them all left-handed. If you don't consider, without any other symmetry, there's no notion of left or right-handed, so you just make them all left-handed. And you can just assign them integer charges if you're considering now a single U1 symmetry. And you can, again, ask for anomalies to cancel. In this case, the anomaly canceling conditions are self-anomaly canceling, sum of cubes is equal to 0, and mixed U. In this case, there's no intrinsic gravitational anomaly, but just a mixed U1 gravitational anomaly, and this is the condition for it to vanish. So you can, just take that field theory and conjecture that it can be realized on a lattice with this symmetry acting on site. And hypercharge, U1 hypercharge in one generation of the standard model is one example. So we'll have things to say about this as well, although not an exactly solved model. Okay. Yeah. Is there a question? Okay. So let me give first maybe a high-level overview for what our strategy is going to be. And this high-level overview applies equally well to 1 plus 1D and 3 plus 1D. Maybe better to keep sort of the 1 plus 1D picture in mind while I'm discussing it, sort of a little more concrete. When I talk about 3 plus 1D, I'll actually be using a slight variant of this, but applies equally well. So the strategy has 3 steps, and I guess another sort of important conceptual point about this strategy is that steps 1 and 2 will only involve one layer. So terminology. I have this sandwich of churn insulators plus one minus one. Let me call that a layer. And then I have a stack of n of those. So all 2n churn insulators, I'll call that a stack, and just the individual 2 opposing churn insulators, and then we can call that a layer. So the nice thing about this strategy is sort of the first 2 parts of it happen all within for a single layer. So it's just statements about a single layer. So it somehow doesn't, the first parts of the strategy don't really even involve the anomaly cancellation, which is something that happens between layers. So it's only, we sort of only use that at the end. So, okay, so what do we do? So like I said, there's 3 steps. The first step is to just look at one layer and realize both of these U1 symmetries. Now, I already said that you can't realize them, and the goal is going to be to realize them in that standalone lower dimension. So in 1 + 1, you really want a 1D model. You're not trying to realize a 2D model with an edge. We're really trying to realize a 1D model like this thing. So we want to realize both of these symmetries microscopically. I already said you can't do that in a way that's on-site. So we generalize, we sort of loosen our restrictions and permit not on-site operators. That's kind of the idea. Let me explain what that is and then give some motivation. So a not on-site operator, think of it like this. So, a charge generator for a U1 symmetry that is on-site can be written as a sum of local terms where each term just acts on a single site. You look at the charge on this site, add the charge on this site, add the charge on this site. That's the definition of a sort of local on-site symmetry. The more general notion that I'll be using, again, has this decomposition as a sum of local operators, but the local operators are not localized to a single site. They're localized to several sites. And actually, in all of the examples that I'll have, I think they'll be localized to 3 sites. And the regions in which these operators act non-trivially overlap. So that's kind of what makes things possible. Now, in general, when operators overlap, they still commute and all sorts of problems arise. But in our cases, actually, these operators will all commute. So in particular, what that means is that you can easily find, this is the sort of infinitesimal generator of some maybe one symmetry. It'll be written like this, but you will be able to exponentiate it easily because everything commutes. And the exponential, the actual group element action, as opposed to the sort of the algebra element, has this form of a finite depth circuit of local unitaries. So this is sort of a standard idea within quantum information theory that, if your degrees of freedom, think of these as, let's say, some local degrees of freedom. This symmetry generator acts by a finite depth circuit, in this case, a depth 2 circuit, where in each layer of the circuit, you apply unitary gates, unitary operators that act on disjoint qubits, sort of local unitary operators that act on disjoint qubits. So this is a sort of an old idea within the study of symmetry-protected topological phases within this matter theory, this idea that enlarging the set of unitaries to these finite depth circuits from just microscopic on-site actions allows you to accommodate some anomalies. So Elsa and Nyack in particular leverage this. Let me maybe just say 2 words about sort of a little bit more about the origin of this, just because I might want to refer back. So in the study, in sort of Elsa and Nyack's work, what they looked at was, in fact, exactly solvable models for the most part of interesting symmetry-protected topological phases, so things analogous to topological insulators. So these are models that are sort of trivial in terms of ground state degeneracies, in terms of they have no anyons, but the only thing that's non-trivial is symmetry action. And so the sort of insight that they had, which, really powerful insight, is that if you consider such an SPT model on a manifold with a boundary, okay, so you have there's a bulk and there's a boundary. The boundary will of course be gapless and protected by the symmetry, but there's an equivalent way to view this whole system. One way is just the symmetry acts on site everywhere, and there's a gapless bulk, and it's sort of connected to this. Sorry, there's a gapless boundary and it's connected to this gap bulk. But what they showed, Elsa and Nyack showed, was that you can equivalently view this by applying some finite depth circuit of local unitaries as basically a decoupled bulk. The bulk is completely decoupled, it's just a product state. You still have a gapless boundary, but under this finite depth circuit, the on-site symmetry has turned into a not on-site symmetry, precisely of this form, acting on the boundary, and then sort of acting trivially as an on-site symmetry in the bulk. So that's kind of, there are two equivalent pictures of the same thing. The finite depth circuit and local unitaries, just think of it as a local basis transformation. It preserves, locality. So max local operators, local operators. It preserves a spectrum. So sort of at the field theory level, low energy field theory level, it does nothing. You have the same spectrum. So that's how this idea of non-onside symmetries arose. Boundaries of SPT phases can be considered as just standalone systems, but with the action of a non-onside symmetry. So similarly here, what we'll do is we'll write down these non-onside actions, and the way that we know that they're doing the correct thing is that we'll actually be able to sort of match them up to SPT phases in a higher dimension, whose dynamics we can, whose response we can probe and see that they indeed pose the right anomaly. So the lattice anomaly will match that of the desired low energy theory. Yeah.
So here, I mean, you had the first line which express the charge as a sum of quasi-local terms, yes. And then you are checking, so you're saying it's not trivial to check the second condition that is that the finite action of the symmetry is also a quasi-local.
Well, no, so if these guys commute, then this follows very quickly.
No, I understand that it follows.
Yeah.
I'm saying, is this something you needed to check, or it wouldn't have been enough to just say the first statement?
Oh, it would have been enough to check the first statement. Yes, say the first statement. The only reason I introduced this is just to connect to this SPT's idea, because they considered only discrete symmetry, so they never wrote infinitesimal generators. They just wrote these things. So just for those of you that saw that work. Okay. Good. So that's the first step. And again, only involved this one layer. Now the second step, again, only involves one layer, is that we don't want to just match anomalies. We actually want to construct Hamiltonians. So, we have this one layer. We have these non-onside symmetries corresponding to vector and axial U1s. Now we want to write down a Hamiltonian that commutes with those symmetries and doesn't break them either spontaneously and realizes the sort of desired low energy theory in the IR. So in 1 plus 1D, the desired low energy theory is the thing that I discussed at the beginning, is single Dirac fermion. That's how these things act. And we can rigorously construct this. In T plus 1D, it turns out that a single layer, one natural generalization you might imagine of the story to 3 plus 1D would be just to replace the 1 plus 1D Dirac fermion with the 3 plus 1D Dirac fermion that also has a U1 vector U1 axial. But unfortunately, in that case, the U1 axial has a mixed anomaly with gravity. And that turns out to obstruct our ideas. And so it turns out that we need actually, instead of 2 wild fermions, we need 4 wild fermions to sort of cancel out anomalies with gravity. So it turns out that this is sort of the minimal layer that we can construct in 3 plus 1D. Now, this is only a heuristic. So this is the only part that we can't do rigorously in 3 plus 1D. We don't know how to write down this Hamiltonian. We have some heuristics for arguing it exists. Say more about that during questions, but we just don't have a rigorous construction. Here, there's a rigorous construction. So in particular here, in the 1 plus 1D case, we know that these non-onside operators really do encode the anomaly because you can just compute the anomaly from the low energy. 3 plus 1D, that step is missing it already. Now, the last step of our strategy, so far, nothing involved coupling the layers together. So the last step of the strategy will have to involve coupling the layers somehow, but we don't couple the layers by introducing interactions between layers. We do things in a much more controlled way. So we already have Hamiltonians, just the ones that I discussed for individual layers. Saturate these anomalies and realize your desired low energy theories. And we add those Hamiltonians over all the layers, and that's basically going to be our Hamiltonian. We're sort of not really going to mess with it too much. But what are we going to do? Well, what's the idea? So this these n copies. So these n copies of the theory have a large symmetry. U1b cross U1a to the nth, mixed anomalies. So one hope that you might have is, well, if I find the U1 in here where the anomalies vanish, maybe that U1 generator will be on site. I mean, maybe I'll get lucky. right? Like there's and generically these are all constructed as non-onsite, but maybe that particular linear combination will be onsite, in which case I'll be done. Of course, life is not that simple. And that's sort of a too naive thing to hope for. It's like saying, if I have a trivial SPT phase, some Hamiltonian describing a trivial SPT phase, maybe its ground state is an exact product state. Well, unlikely. But what you can hope for in that case is that the ground state is sort of a symmetric finite depth circuit away from being a product state. So in other words, can be conjugated by a symmetric finite depth circuit into a product state. That's sort of generically believed to be true for SPT phases. So here, likewise, it turns out that our non-anomalous generator will not generically be on-site, but we can explicitly construct this finite depth circuit that conjugates it into an on-site operator. And I should say here, we were really motivated by this really beautiful paper by Sahan Signatri and Wilbur Shirley, where they did this in the case of discrete symmetries. They sort of really explicitly showed how to construct this symmetry disentangler. And so just kind of leverage their ideas and sort of apply them to U1. Kind of a very natural direction to go. And so the point is that, look, if you can make this non-anomalous generator on site by this conjugation, then you can just conjugate your original Hamiltonian commutes with the non-on-site guy. Well, if I conjugate my Hamiltonian by the inverse, then it will commute with the on-site guy. And then now I'm done. I have some Hamiltonian, has the same spectral properties, because finite depth circuit conjugation doesn't affect spectral properties. Still local Hamiltonian, because this is a finite depth circuit of local unitaries. Commutes with my on-site symmetry. I can gauge this symmetry if I would like, or not. But that's the construction. Any questions at this point before I discuss the details?
Maybe the H prime has some arbitrariness, or is it?
H prime has some arbitrariness. So we construct H prime explicitly for 1 plus 1D. There's just some exact Hamiltonian that you can write down that you can solve exactly that commutes with the symmetries.
So if I think W construction of W is related to the construction of X in step 1.
Yeah, exactly.
So once you fix that in step 1, W is almost unique.
W is fixed. Yeah, exactly.
W is unique.
Yeah, W is unique. W doesn't depend on the choice of Hamiltonian.
W is okay.
This entangles the symmetry. There's like a kinematic. Yeah.
So H is going to be some Hamiltonian in terms of fermions that has a finite range, right?
Yeah.
So the Nielsen-Ninomia theorem is going to say that if I write that, it's going to have doublers.
If you write a free fermion.
In terms of those fermions, it's going to look like it's vector law.
Well, this is not a free fermion Hamiltonian. This is intrinsically going to be interacting, yeah. And in fact, so maybe I should say, since it's brought up, it's on my next slide, the Hilbert spaces here that I will use, might as well just move on to it. The Hilbert spaces will not just be simple finite dimensional Hilbert spaces, not really just, the usual Hilbert spaces you have in a fermionic tight binding model. It'll still be tensor products of Z2 graded Hilbert spaces, so they're fermionic in that sense, but I will need sort of in addition to just like a 2-level fermionic system at each site, I will also need a U1 rotor. I design a U1 rotor, okay. And that makes everything interacting, yeah. But I mean, it's still a fermionic Hamiltonian in the sense that there's fermion parity and Z degraded. And in print, yeah, that's right. Yes, okay, so let me move on to these caveats. So first of all, we constructed only the bosonized version of this theory, but actually that's not so big of a deal. I actually have worked with my student now where we have an intrinsically fermionic Hilbert space in 1 plus 1D. In 3 plus 1D, we have to work with the fermionic Hilbert space from the get-go, and we do. The important point, sir, is that my Hilbert spaces are not finite dimensional. My Hilbert spaces are rotors. So they're basically L2 square angle functions of a periodic variable. That's an infinite dimensional separable Hilbert space. You can think about an angular momentum basis. Our exact construction in 1 plus 1D kind of really requires these rotors. Now, you can imagine taking such a rotor and truncating it at some finite but large angular momentum and throwing away, just imagine projecting the Hamiltonian down onto only terms that involve angular momentum up to some finite but large level. That would give you a finite dimensional Hilbert space. That would immediately, I think, break exact solvability of our model. But it should still realize the same theory, and you could sort of argue from a field theory perspective. And from a field theory perspective, truncating at this very large angular momentum level should just introduce a small perturbation that's symmetric, and so should be irrelevant. Another important caveat is that our disentanglers are kind of weird. So this W that I mentioned, it's a complicated unitary. I'll show an expression. But in particular, it involves pieces which, you can even think about this for a single rotor, this complication for a single rotor. You can imagine a unitary that's diagonal in the rotor basis, so just multiplies by some function of this angular variable phi, but the function is discontinuous in phi. Okay, that looks bad, but it's fine. It's a fine unitary on this Hilbert space. It's a bounded operator. What's wrong with it is that it does not preserve the domain of the Hamiltonian operator. So you can even understand this for a single particle on a ring. Single particle on a ring, Hamiltonian p squared over 2m. That's an unbounded operator. It's not defined everywhere in Hilbert space. It's defined on a dense subset of the Hilbert space. The states of finite angular momentum, for instance. If you multiply, if you conjugate that Hamiltonian by some e to the I f of phi, where f is discontinuous in phi, the angular momentum states, finite angular momentum state is going to have infinite energy under that Hamiltonian. But that's fine. It's just the wrong domain. So there's a different, so the naive domain that you would associate with just, p squared over 2m Hamiltonian, just free particle on the ring, is not the right domain for the Hamiltonians we'll write down. The domain, the domains of our Hamiltonians will have, if you view them as wave functions of these angular variables, they'll have discontinuities. It's just something one has to look. Caveats out of the way. Let me just.
Does that mean that you cannot truncate the Hilbert space?
First, conjugate by the unitarian truncate there, and then conjugate that. Yeah. So let me discuss this construction in these three steps. In 1D, Maddie told me that I should call this the modified Delaine model. So apologies. It's a modified Delaine model. So in 1D, and again, there's a caveat about bosonic, so I'm going to construct the bosonic version of this. The degrees of freedom are real valued degrees of freedom living on these black dots, and integers living on you can think of them as the links between the black dots. So one way to think about this is this is like you have real value degrees of freedom, but you're gauging the integer translation symmetry of R. But you don't have to think about it that way. You can just think about it, okay, you have some wave functions of these guys, phi's and n's, and they satisfy this Delaine constraint. So the Delaine constraint is this. This is basically sort of Gauss law associated with gauging the Z symmetry. There's actually a nice, there's a lot of indices floating around. There's nice compact sort of co-chain notation, if you're familiar with that, which, basically just drop all the indices and kind of, you don't really lose much information, in that notation, the Delaine constraint is just this. So in this Hilbert space, so this is not a tensor product Hilbert space, and we'll get back to that. I promised the tensor product Hilbert space is not tensor product Hilbert space, but nevertheless, so this was, introduced a nice paper by Maddie and Mong. I have the reference on the next slide. You can define vector and axial vector symmetries in this way. So this is just the usual compact momentum of the rotors, and the axial symmetry is defined in this way. And okay, it's just some non-onsite thing, right? This is a not on-site thing. This one's on-site, but this one's not on-site, and that turns out to be enough. And so Maddie and Meng sort of had a nice paper where they introduced this, and they pointed out that, look, you can write down a Hamiltonian in this Hilbert space that commutes with both these symmetries. and just flows to a Ledinger liquid or a free compact boson. Okay, so it's like it's not that hard to write down a Hamiltonian that gives you flows to a free compact boson. Just write down the XY model, but this Hamiltonian has a special property that it has an exact microscopic, albeit not on site, axial symmetry. So the winding is preserved exactly at the microscopic level, but you need this sort of Villain formulation. So this was very nice work. It's not a tensor product Hilbert space, but that turns out to not be a huge deal. It turns out that you can apply this. You can apply a finite depth circuit. This is not the circuit W that is going to disentangle the symmetry. This is kind of a step before that. You can apply a finite depth circuit, which I'm calling C here, which disentangles the Villain constraint. The formula is kind of a little bit complicated, but effectively what it does is it disentangles this Villain constraint. So the Villain constraint that I had previously, which sort of involved, shifting phi by an integer and shifting the adjoining links by a corresponding integer, that gets mapped when you conjugate it by this Villain disentangler to just a simple shift of phi. And so the wave functions that were invariant under the Villain condition now just become wave functions that are invariant under individual shifts of phi. So in other words, the phi's become true rotors. So you have rotor variables phi, and you have integers n, which you can think of as a dual rotor. So you just have a bunch of rotors. That's your Hilbert space. The funny thing about this Villain disentangler is there's this funny notation, floor ceiling. So this is the integer closest to function. So this is integer closest to x. This is a discontinuous function of x. It's 0 between -1/2, then 1 between 1/2 and 3/2, etc. It's like a floor function, but kind of symmetrized with a ceiling function. So this was introduced by DeMarco and Wen in another work. It's also motivated us to study this stuff. So this is where these discontinuities, the angular variables, first start to show up. Okay, so at the end of the day, we can just conjugate Nadi and Mong's construction and get things that work in a tensor product. We just conjugate everything, the symmetries, the Hamiltonian, everything. Still has the same thing. Okay, so that's steps 1 and 2 in 1D. So the crucial third step, how do we disentangle the symmetry? How do we find the symmetry disentangler? So in order to do that, like I said, we need a stack. Okay, we have a stack of n. So for the T450 theory, n is equal to 2. Each one of these realizes a left and a right mover. It's just the Hamiltonian we just wrote down. And I'll need some ancillae, it turns out. So I'll need some additional rotors, which I've drawn here in blue. And this is actually part of Sahan's construction as well, which is really copied it over. These are periodic variables. And so, I already have a Hamiltonian on these guys. These guys, I'm just going to literally put them into a gapped product state of at zero angular momentum. So they're just kind of dead as far as the low energy theory is concerned, but they're important for defining the symmetry disentanglement. Okay, so now I have so what's my process? I have some anomaly free U1 that sits inside here. It has some expansion in terms of these layers. So alpha is the layer index, some integers QV and QA. And I added these ancillae, so I'm gonna, maybe ancillae carry charge 1. So the ancillae are these again. These are just dead because the Hamiltonian, they're completely decoupled, and the Hamiltonian just really forced, it's a gapped Hamiltonian that forces these ancillae to the zero angular momentum. Anomaly cancellation condition just says that there's a sum of squares or difference of squares, which says in terms of vector and axial variables, it's this inner product is equal to 0. And our goal now is to find the symmetry disentangler W. Okay, how do we do that? It's not very enlightening. I'll just say that off the bat. You just write one down. So W, the symmetry disentangler, is a product of two other operators, one of which, this capital phi, is diagonal on the phase basis. The other one is, the other one just looks like this. We call it a shift operator. It looks a little better in cochain notation. It's a complicated thing. It's not very intuitive, but let me try to convey a little bit of intuition for what this is actually doing. If you look at the form of these operators, and I'll look at the compact cochain version, which just drops it's the same expressions with indices dropped, so it's a little clearer to read. What are these operators doing? The S operator, what it's doing is performing shifts of phi So it almost looks like it's doing the vector part of my non-anomalous symmetry, but it's a spatially dependent shift where the amount that you shift by is depends on the value of the ancilla at that location. So here that you have a theta j. So the ancillae kind of, the configuration of these ancillae, which you should think of as rotors, tell you in this disentangler how much to rotate by. Okay, and similarly in this phi, the other piece of the disentangler, you have this term here, which again is a spatially dependent sort of ancillae controlled axial part of the symmetry. This is the kind of what the axial part of the symmetry did. And there's this additional piece here, and this additional piece kind of needs to be here because otherwise this expression doesn't make sense. This expression needs to be invariant under individual shifts of phi. The operator is just multiplication by this. Phi is an angular variable. If I didn't include this piece, it just wouldn't be a well-defined operator. So that's why I did this. So yeah, you should think of this disentangler as performing a controlled operation where for any given state of ancillae, and ancillae I mean in the phase basis now, so well-defined values of theta, I perform a local rotation by my non-anomalous symmetry by that amount, by theta, essentially. So it sort of makes sense that this would disentangle symmetry because if you think about it, what you're doing is you're performing, or let's say, doing the inverse first. So you're performing an inverse rotation by your symmetry U1 in some spatially dependent way, governed by theta. Then you are applying the on-site, put these W's on the other side. So let me show that conjugating the on-site symmetry recovers the original symmetry. So if I do a spatially dependent rotation like this, it's like I'm trying to do my non-on-site symmetry in a spatially dependent way, then I change my ancillae and I undo, but with the new values of ancillae. And so there's a cancellation up to that overall shift, which just performs the global symmetry. Okay, that was probably not very enlightening, but in any case, you can just explicitly check, just do an explicit computation. And what you find is actually very cute. So if you just take this W, complicated W that I wrote down, and conjugate this non-on-site Q, it becomes this on-site Q times this fudge factor phi prime, where phi prime is an operator that's diagonal in the phase basis, and it's the identity precisely when the anomalies cancel. You see there's a sum on QA, QB, which is the anomaly cancellation condition is just that this is zero. So this works precisely when the anomalies cancel. That's kind of the gratifying thing. So that's the symmetry disentangler. Are there any questions? Okay, so I know that those formulas were not maybe this enlightening, but are there any questions about this? Okay, so let me move on to talking about 3+1D. But before I do that, let me do something in 1D which will generalize naturally to 3D. So in 1D, I mentioned that so I defined these axial and vector U1 symmetries, and in that case, I didn't really need to have any kind of lattice diagnostic of the anomaly because one can write down and wrote down an exactly solvable Hamiltonian, which reproduces a field theory with the anomaly U1. So you don't have to do anything, but it's still nice when generalizing to 3D to see how you would actually see that there's an anomaly. Just if given this non-onsite actions on the lattice, how do you see just from these symmetry actions, not given any Hamiltonian, that these have the right mixed anomaly? And so there's several ways to see it, but one sort of particularly appealing one that will generalize to 3D is this, again, sort of based on this Elson-Nyack prescription. What you do is you take your axial generator, you restrict it to an interval, so just keep the terms inside an interval. So this is the truncated axial generator, and you exponentiate that. And so if you do that, you'll see that you have some terms which are integers, this and this, and you have some terms that telescope. The terms that telescope tunnel charge from one endpoint to the other. Okay, they just tunnel charge, pumps charge from one endpoint to the other. This turns out to be the hallmark of the mixed anomaly between these two symmetries. You also have to consider sort of the reverse process, but here the vector symmetry is on-site, so it doesn't. There's the nice continuum field theory intuition for why this is the right mixed anomaly. I mean, just imagine that you have a Dirac fermion in 1+1D. You have the axial and the vector symmetry. You can imagine the following. Imagine just breaking the axial symmetry and gauging the vector symmetry. The effective action is just has this this theta term. And then when you act with this truncated axial symmetry, that amounts to shifting theta by 2 pi. You shift theta by 2 pi, sort of slowly in this action. You can integrate this out to the boundary and you get a charge at the boundary. This is very, very simple stuff. But this is what generalizes nicely to 3D, which is why I wanted to show it. So in 3D, the story is a little more complicated and the formulas get more complicated. I will only write the cochain formulas because the indices get really hairy. And in 3D, because there's no bosonization, I have to work in an intrinsically fermionic Hilbert space from the get-go, but I'll actually start by working in a bosonic Hilbert space. So this is a different anomaly structure. It's not the one associated with the sort of 4 wild fermions that I promised, but I'll decorate it with fermions later. So in 3+1D, the geometry is also more complicated. So in 3+1D, I don't just have a line. I instead have a simplicial manifold in my lattice construction, okay, because I need a lattice structure. So I have some spatial manifold M3, and to get a lattice Hilbert space, I can do a simplicial decomposition of this manifold. This actually works with also just the ordinary cubic lattice. All this algebra turns out to generalize to just an ordinary cubic lattice, but somehow it's easier for me conceptually to think about a simplicial complex. So the degrees of freedom are still rotors. They live at vertices of this simplicial decomposition. So just imagine a bunch of tetrahedra. I'm still calling them phi. And my manifold has something called a branching structure, which doesn't really matter what it is. It's basically an ordering, a consistent ordering of all the vertices of each tetrahedron. And this branching structure allows you to define lattice level cup products. So cup products are just lattice level generalizations of differential forms. So with all this structure, it turns out that you can write down an axial generator that looks like this. Okay. Now, I don't expect anybody to sort of figure out what this formula is doing in real time, but it can give you some geometric intuition. So what was the axial generator doing in 1D, in one spatial dimension? It was just counting the winding of this field phi. It's just counting, it's just the winding number symmetry. I have to mix it out with compact momentum. What is this guy doing? So what this guy's doing is the following. If you have a configuration that's diagonal on the phase basis, okay, so just imagine, something like a superfluid, so phi, well-defined value of phi at each point in space. You can imagine that you have just an ordinary superfluid, or you can imagine there's some vortices in the superfluid. Okay, so there's some winding of phi around these vortex strings, and there's some vortex strings, and these vortex strings might be in a topologically non-trivial configuration. So then it turns out that this axial charge, what it measures is the self-linking number of that configuration. Self-linking meaning you take the configuration of vortices and you push it off infinitesimally, and they actually, there's a subtlety there. You use the branching structure to define the push off. You push it off infinitesimally and you compute the linking number with itself. That turns out to be the eigenvalue of this operator on that state. Just like winding number was the eigenvalue of the axial charge in 1D. Here it's the self-linking number of the vortices. Why is that the right thing to look at? Why is it the right thing to look at? So the reason that this is the right thing to look at is, again, you can use this, there's better arguments, but you can use this sort of continuum intuition. You can, again, truncate this axial generator now not to an interval, but to a three-dimensional ball, and apply a 2 pi axial rotation inside that ball. What do you get? Well, what you get is, again, you have this term that disappears because these are all integers, and this term kind of telescopes. It's a total derivative. That's what the generalization of telescoping is to these products. And what this operator does finally is, instead of pumping a charge out to the endpoint, it pumps an SPT phase with non-zero Hall conductivity out to the two-dimensional boundary of this three-dimensional region. And this is actually this wave function for this SPT was actually written by DeMarco and when he used this whole notation, and that's sort of what inspired us to look at some of this stuff. But that's the generalization. And this, yeah.
What is this notation with the
this?
Yeah.
This is integer closest to. So this is it's a discontinuous function.
Of the lattice or in the continuum?
This is a formula on the lattice. This right here is the formula on the lattice. This is a formula on the continuum, but this is a formula on the lattice. Yeah, this is a formula on the lattice. And yeah, so this is a function that was written by DeMarco and Wen. It's a wave function for rotors that just constructs a 2D bosonic SPT state. And I remember seeing it at the time and just thinking this is like very bad, like the discontinuities and so something's wrong with it, but there's nothing wrong with it. It's perfectly fine and has the right Hall connectivity, and they checked it. So again, so we generalize from pumping charge to pumping Hall conductivity. That's the generalization, and that comports with this continuum intuition. Again, if you have axial and vector symmetry. Okay, so now we're in the bosonic world. So this, what do I really mean by this? Well, it turns out that you can still imagine a mixed anomaly between 2U1 symmetries that shifts, where the axial symmetry shifts theta. And then when you integrate that out to the boundary, you get this kind of bosonic SPT response. So it sort of comports with your continuum intuition. And okay, this is some more about the analogy. So here I've written the anomaly inflow SPT action. So in 1+1D case, remember it was this dA cup AV. In 3+1 this is the 2+1 dimensional anomaly inflow action of the 1+1 dimensional gapless theories. This is the 4+1 dimensional anomaly inflow action of the 3+1 dimensional gapless theories. This one just has an extra wedge product. And this again comports with this intuition that I just described, this pumping intuition. Okay, so we find some lattice non-onsite actions, which seem to have the right mixed anomaly, and they're still bosonic, so we have to fix that. But one thing that I will do now is I will take a slight detour from the strategy in 1+1D. So in 1+1D, remember the next step after you wrote down the non-onsite symmetry actions was to find a Hamiltonian that respects them. So we can't do that here, unfortunately. We don't know how to do that. So I'll do something slightly different. What I'll do, which is formally actually, I could phrase it entirely in terms of sort of the strategy I mentioned at the beginning, but it's just conceptually easier to talk about it this way. So what I'm going to do is, these non-onsite actions that I just defined of U1 vector and U1 axial, and these three-dimensional complicated lattices, they look like the boundaries of certain 4+1 dimensional SPT phases with this anomaly inflow action, using this Elson-Nyack idea. So there's sort of a one-to-one unitary locality preserving mapping between these two settings. I can either talk about strictly 3+1 dimensional lattice systems with non-onsite symmetries, or I can talk about the boundaries of gapless boundaries of 4+1D commuting projector SPT. So it turns out that the bulk here, which allows you to make everything on-site, is a nice commuting projector, well-controlled commuting projector model. In particular, has zero correlation length. So it's an exactly solvable SPT phase. These are equivalent pictures. So what I should do really is work here and construct a Hamiltonian that's invariant under the symmetries here, the non-onsite symmetries here to carry out my program. But what I'm going to do instead is work on this side, which is formally equivalent, and I'm going to try to construct a Hamiltonian on this boundary. Again, it's the same thing. There's a symmetry, there's unitary equivalence between these. So my goal is to take this SPT, commuting projector, has this anomalous boundary, construct a Hamiltonian. So I can't do that exactly. Oh, sorry. First of all, before I do that, the fermions need to come into play. I promised the fermionic Hilbert space. So we found a nice way to decorate the lattice with fermions. So now it's getting really hairy. There's rotor degrees of freedom on vertices, and there's additional intrinsically fermionic integrated Hilbert spaces, two-dimensional, written in terms of these so-called Majorana fermions. So that's how the Hilbert space is modified. We also need to modify the generators. So it turns out that the U1 vector generator is not modified, but the axial one needs to be modified so that an axial rotation by pi is fermion parity. So if you remember this theory that I mentioned of 4 wild fermions in 3+1D, it has that property. The axial rotation, if you axially rotate by pi, you get -1 with fermion parity. So it better have this property. So we found this way of modifying the axial symmetry. It's actually really nice. And it's related to these ideas in 3D SPT phases, where this axial generator, remember what I told you, the axial generator computed the self-linking number of the vortices. And so when you evaluate it at pi, it just -1 to the self-linking number. And in order for that to become fermion parity, we have to find some way of canceling that by using this additional fermionic degrees of freedom. And it turns out that you can do that by decorating Majorana chains onto sort of in a way that's controlled by the vortices, and then constructing that by linearizing the Majorana. I don't have time to go into the details here, but it's a pretty nice construction. And that now becomes a fermionic Hilbert space. You still have the same inflow action, but now it's a fermionic theory. The goal now, remember, the goal is to find a Hamiltonian. That's the second step. And I'm going to do on the left side rather than on the right side. And the way that I'm going to find this Hamiltonian.
Okay.
Yeah.
So the anomaly is still the same anomaly.
Right.
How you modify the symmetry action so that it's a Z2 parity.
Exactly. That's right.
So U1 transformation in the bulk is on site.
The U1 transformation, which U1?
So you want to now take the 4+1D system and then
Yes.
repeat the construction, but then
Oh yeah, that's right. And then 4+1, everything's on site. Yeah.
everything on site, so you're just now, from now on, you're just working on site.
Yeah. So this non-on-site idea will come back in one
Will
more.
come back.
It will come back in step. It kind of has to come back in step 3 because the step 3 was disentangling a non-on-site thing. So if I have everything on site, what do I mean by that? But we'll show you how it comes back. Okay. It's just same thing. Yeah.
So I guess the idea here that the bosonic anomaly would be, is it correct to say the bosonic anomaly is actually cancelled by some nominal fermionic degree?
Canceled in. I mean, the bosonic action of the axial generator at pi. When you rotate by pi, that's canceled by the fermionic piece that I add in. Canceled in a way that the total thing gives you fermion parity. It can be canceled to the identity, but it gives you fermion, which is actually what you need. Right. So that's
Then the fermions are decorated in this kind of Majorana chain decoration on the vortices.
yeah, exactly. Yeah. That's right. Okay, so I have my Hilbert space now. Now I need to write down a Hamiltonian here. Okay, I can't do that, but I'm going to give a heuristic, and the heuristic is actually going to be on this side. So here, what I would have needed to do is write down a Hamiltonian that reproduces the right low energy theory. Here, the idea is that what I'm going to do is I'm going to take this anomalous boundary, and instead of working with it directly, what I'm going to do is introduce yet another system, which I've drawn in red now, which is a free fermion system. And it's just the usual domain wall idea of free fermions. So it's basically an 4D integer quantum Hall state of fermions. It has wild fermions in the boundary. It has the theory that I want, these 4 wild fermions with these charge assignments. It has the same inflow action, and I'm just going to stack one on top of the other. Okay, and I'm going to cross my fingers, and I hope that I can gap out this boundary. Okay, that's where the non-rigorous step comes in, but it only involves this sort of single layer. So you can imagine, in the context of my original strategy, you can imagine this extra stuff as like additional sort of ancilla degrees of freedom that I'm using in order to construct the theory that I want. I can sort of throw in as many ancilla degrees of freedom as I want, but at the end of the day, I gap this guy out, and my desired IR theory appears here. Okay, so if I squash everything down along this dimension, I've got my desired theory here. Now, yeah.
So I guess you haven't specified what happens on the boundary of that bosonic plus
down here. Yeah, exactly. Well, so I haven't. Yeah, that's the missing piece. So I know it has the right lattice anomaly, and so so I hope that it can be gapped against something else that has the same anomaly, and that's where the heuristic comes in. And I can say more about that. We have some better. Yeah, but now what's left is that I still have gapless degrees of freedom down here, and that's expected because I still haven't used my symmetry disentangler. Like it can't be magic. I still need to use my symmetry disentangler. But now I use the symmetry disentangler effectively, essentially the same as before. So now the idea is that this is still the boundary of this commuting projector SPT. I can using this Elsoniac way, I can think of it as a non-on-site symmetry action strictly in 3D. Then I can introduce my stack, look at my non-anomalous symmetry, disentangle it into an on-site symmetry. And what do I do with that? Well, once it's been disentangled into on-site symmetry, I can write down gapping terms and just gap everything. I can gap out all the degrees of freedom. Once I have a Hamiltonian that's symmetric under U1 on-site symmetry, And all I care about is maintaining that U1 onside symmetry. I can trivially gap the system out just by putting sort of each local degree of freedom in like a zero angle random state. Yeah.
Should I think of this as one layer, as making a one plus one example?
This now involves, so this is all one layer, but now this last step that I talked about will involve coupling between the layers. So now you imagine several of these, and this last coupling, that I just mentioned, this gapping out will involve all the layers, because it's effectively using this conjugation by the symmetry disentangler. So this is kind of very reminiscent to this symmetric mass generation idea where you try to gap out doublers. That's kind of what this is doing effectively. But what's special about this is that the gapping out procedure here is happening in a completely controlled way, because this is a zero correlation length model. So this thing that couples between the different layers, that's exactly controlled using this symmetry disentangler idea. And I should say that Ryan actually found this symmetry disentangler. It's a lot more hairy than the 1 + 1 D1. It uses and kind of you can kind of imagine that it has to be, because it somehow has to be non-trivially use this condition. So how does that come up? So you can look at our paper for the exact. Okay, so I'm over time. Let me just say the last thing, which is that this kind of construction that I just outlined applies to an interesting example, which is just a single generation of fermions in the standard model, assuming a sterile neutrino. So I have 16 viral fermions. So I can group the quarks into, so just turn off all the other gauge fields and just look at the U1 hypercharge as a global symmetry. So there's 3 quarks, and there's the lepton sector, and they each have 4 fermions. And it turns out that the U1 hypercharge can be expanded as integer combinations of precisely these generators that I want. And obviously the anomalies will cancel. So this construction applies to that. Okay, so here's just some words about what I already talked about, the heuristic. And again, I have more to say about that. And then let me just conclude with future directions, which is, can we do sort of SU2? Can we deal with the Whitman anomaly? Mixed U1, SU1, we have some preliminary work on that. Obviously, dealing with infinite dimensional Hilbert spaces is bad. How can we truncate to finite dimensional Hilbert space? I already mentioned some things on those lines. And obviously, numerical simulation would be great. That's related to this. But since I'm already over time, let me end here. Thanks.
The example of the standard model that you well is the inflow mechanism. How should I think?
Well, so I mean, it's this it's still this picture. So I break up the 16 fermions of one generation of standard model into groups of 4. Each group of 4, I define this U1 vector and U1 axial generator like this. So for instance, I can take the leptons, assuming there's a sterile neutrino. There's 4 leptons if I count by viral fermions. So there's sort of 4 U1 symmetries there, 1 associated with each vial. But I only want to take this particular combination. So I want to look at only this or this generator or any linear combination of them. So that's 2-dimensional subspace of sort of the 4 possible U1s. When I take those 2 U1 symmetries, that's where the inflow mechanism happens, because I have an anomaly inflow SPT phase of those 2 U1 symmetries. So that's a non-trivial SPT phase, but the point is that once I consider all 16 fermions, the anomalies cancel. And this construction just kind of lets you do that symmetric mass generation in some kind of controlled way, simply because down here, this is all the same inflow anomaly SPT phase, but this is a commuting projector version of it. And when a commuting projector is exactly solvable, it has 0 correlation length. And so you can sort of write down this is all strongly interacting down here, but exactly solvable. So
does it allow to write and find the lattice?
Well, so it would, yeah. So the only missing piece in finding a lattice is finding this gap interface between these 2. That's where the heuristic comes. And you can say that's a big problem. I agree. But it's not as big a problem as having 16 vial fermions and trying to play games. This is, only 4 vial fermions. Something, yeah.
So when I actually couple a dynamical gauge field
Yes.
I have to do that all the way down the stack, right? Because otherwise I violate gauge theorem.
That's right. You have to do that all the way down the stack. Yeah, everything's charged under this.
So I have to couple that to the commuting projector model.
Correct. Yeah. Absolutely. Yeah. Mhm. Yep. Yeah. So maybe that's challenging for numeric.
So if I have a smaller number of wire fermions and I cannot realize it this way, like by decorating my arenas like vortices of U1.
Like a smaller number, like what do you have in mind?
I don't know, 1 or 2.
Yeah. Well, so I mean, you want to have right. You know, in order to realize these with non-on-site symmetry actions, you have I think you have to have mixed anomalies with gravity canceling, and so that's a condition. But there are examples where you can have the mixed anomaly with gravity cancel. And so there are examples of like, you know, where all anomalies cancel, mixed anomaly, gravity, and self-anomaly, but it's somehow still not, you can't group them into groups of 4. You have a number that's not multiple of 4. So that, you know, so there's something special about the U1 hypercharge as it makes it amenable to this mechanism. Maybe there's a generalization of this mechanism that works for any anomaly free thing, but here this only works for these specifics. Any question?
Now let's time the question.